Thank you. Thanks to the organizers for bringing us together here and for inviting me to speak. I'd like to start the whole series of talks by just reminding us what brings us together and why we even have a conference series called Amplitudes. And I guess as we all appreciate, what we're doing with Amplitudes is we're exposing different kinds of simplicity in scattering amplitudes that we've found useful. And what advance the slide just with the arrow, please. Okay, thank you. And where many stories begin, and the story of, I think, our community as such arguably begins, is in n=4 super Yang mills. So that's what I'd like to bring our attention to and review some of where we have come from as a community. So one reason that we study n=4 super Yang mills when we're looking at studying scattering amplitudes is there's a big motivation for precision computations coming from the needs of QCD. And people studying QCD has realized at some point that studying gluons, the interactions of gluons and light quarks is very, very much like studying gluons and gluinos related by supersymmetry. Difference in tree level amplitudes is you only have to adjust the color factors, and the structure of the tree amplitudes is very much the same. I think this is familiar to many of you, at least. So supersymmetry tricks can be carried over to QCD, and this had very practical applications. Now, as many of us also appreciate, n=4 super Yang mills is a theory that's fascinating in its own right, is different from QCD, and has a lot of extra structure. So here I'm just pointing to two review articles that will cover these whole stories for people who are not so familiar. So in n=4 super Yang mills, where there are many extra symmetries, you've got the structure of supersymmetry and, of course, dualities. You can study weak coupling, strong coupling. And we tend to focus on 4 dimensions and the planar limit of n=4 super Yang mills, where you can see a lot of this extra structure. So you can explore this rich theory in its own right. So whether you want to do something useful for particle physics or really probe quantum field theory in a deep way, profoundly, you come back to n=4 super Yang mills in the study of amplitudes. And so it's been called the hydrogen atom of gauge theories for this reason. So where we come to is amplitudes, which we are interested in planar n=4 super Yang mills. They have plenty of structure. So this gives us inspiration to tackle real-world scattering problems, which by now even extend into classical gravity, in a more recent twist. And you use amplitudes and the structure you find in scattering amplitudes to contemplate quantum field theory very, very broadly. What is the structure of quantum field theory as such, even if you want to think beyond just computing the next order in perturbation theory. So some examples of structure that I have in mind, and coming back to n=4 super Yang mills, is a part of where the story of our community also starts is in exposing a duality of n=4 super Yang mills with twistor string theory, which gave some very interesting new ways to compute tree amplitudes. Looking beyond tree amplitudes, if you want to start talking about loops, then in n=4 planar super Yang mills, you find a highly restricted set of master integrals. So if you want to start probing the loop expansion, you have extra structure to constrain those loops, and we'll see some examples of that shortly. Then getting into more advanced kinds of mathematics, you find that amplitudes are related to positive Grassmannian geometry, and there's also some structure related to cluster algebra. And the point of studying this kind of structure in n=4 super Yang mills is that I think to some extent, everything that you find there, even though it's a highly symmetric and very, very special theory, many of these ideas, all of them to some extent, can be transferred to other theories, which is why we keep coming back to n=4 super Yang mills. So from the structure we see in amplitudes, of course, that exposes the simplicity that I'm focusing on, which then for practical applications can lead to shortcuts and new methods for computing amplitudes. Okay, also it seemed appropriate to start discussion of amplitudes looking back to where we came from, of course, by coming back to the famous Park-Taylor formula for maximal helicity violating amplitudes for gluons. I realize, I know this conference was preceded by a school, and there's, of course, the basic study of amplitudes, which I think many of you know will start essentially with this amplitude. May not have been covered last week. So this, we can already appreciate a lot of structure here. It exposes, it was conjectured in the first instance from exposing the basic singularities in terms of what appears in the denominator that can go to 0 in a tree-level amplitude. Once you start thinking about twistor geometry and you map this expression, which is given in terms of spinors, or helicity spinors, you map it over to twistor space, and you see that this kind of amplitude is supported on a line in twistor space. And this is the starting point of exploring the structure of amplitudes geometrically in twistor space. As such, then this expression, which is a full amplitude, turns out to become a building block for other helicity amplitudes in all kinds of on-shell methods, and they are a very, very basic building block. And this is written for just gluons, tree-level amplitude. You can easily extend this to a full superfield, which has gluons as its components, if you like. So what I'm doing lately is I'm also going back to my roots, as many of us have dabbled in or started in n=4 super Yang mills, and that's the case for me as well. And so I've recently found it interesting to revisit some ideas about one-loop amplitudes even in n=4 super Yang mills, applying lessons that we've learned much more recently. So I'll try to take you on a little tour of my thought process on this. So going back to the beginning, my beginning in amplitudes, which was 2004, what we understood then, is I mentioned you get a highly restricted set of master integrals. So it was already known then, actually from the 1990s, that in n=4 super Yang mills, rather than requiring one-loop amplitudes with master integrals with various numbers of propagators, it's sufficient to focus on, or to take only boxes. So only boxes, and you can have just one leg at a corner or multiple ones. In principle, you need all of those, but then that's it. So in 2004, there was more understanding on how to produce the coefficients. So the master integrals, those boxes, had been calculated. I'll show you a bit more about those shortly. The coefficients were a bit of a mystery, and it was quite an art to extract what these were. And one big development is that it was easy to obtain these from quadruple cuts by just applying an operation that puts all 4 propagators on shell for the master integral on one side and for the full one-loop amplitude on the other side. When you do that to the full amplitude, what you've got left at the corners are still full amplitudes, but then at tree level. And then to get the coefficient, you just need to divide this by this. So that it requires knowing all about the structure of the master integrals, and it requires having good control of or at least being willing to say, we understand what the tree level amplitudes are, and then we can feed them to get the coefficients, and then we can reconstruct our whole one-loop amplitude. Okay, good. So then that seemed for a while like the end of the story, and that was the end of that story for a little while. There was a big wave of developments around 2008, 2009, and this extended this story now explicitly to super amplitudes. So I mentioned if you want to talk about n=4 super Yang mills fully, then besides just focusing on gluon amplitudes, if you want all the other components and their amplitudes at some level, then you can put them all into components of the superfield and compute superamplitudes. And this was done then in a whole series of work. And for this, I'm just referring to the book by Wang and Huang, which basically summarizes the story very nicely. They can work directly in the full n=4 theory. Once you put together the components in a superfield, you have a new appreciation for the separating positive and negative helicity components of gluons, because these are also just separate components of the superfield. The reason this sort of came back and merited a new look around that time, it was motivated by a newly discovered duality with Wilson loops, which is part of the rich structure of n=4 super Yang mills. And so as a consequence, looking at superamplitudes, there were new uses of, I guess, what was just introduced as the dual superconformal symmetry and momentum twisters. These are still ideas that yield fruit today in many ways. And shortly thereafter, then there was new interest and appreciation of amplitudes and their expression in terms of Grassmannian geometry, and then eventually the Amplitude-Hedron geometry as well. And since then, there's been a lot of good progress in studying amplitudes in n=4 super Yang mills. So some of the amplitudes have been computed to very high loop order. Now this is mostly done in the MHV helicity case. To some extent, some NMHV. It would be hard to do anything that's really fully helicity independent or goes very far beyond that. So master integrals beyond one loop are also, well, at one loop and beyond, have also been pretty well classified. There's a lot of progress in understanding those. A recurrent issue is the infrared divergences of the theory. So this needs to be controlled. Now, it's very common in order to do this, there are many approaches you can take. Dimensional regularization is one that I particularly appreciate because it's one that's also very commonly used outside n=4 super Yang mills and doesn't rely on other symmetries. So if we're going to take lessons and try to carry them over to other theories, that's a reason that I like dimensional regularization, but there's also master regularization, other issues, other solutions like taking ratios that happen to be finite, or certain ways of just factoring out a known divergence. Now, whenever you apply any kind of regularization, this does tend to spoil all the symmetries you have of your theory. So that's why some work has been done into controlling these divergences in a way that's as compatible as possible with the symmetries. One other approach is just to talk about integrands and delay the problem of worrying about these divergences that will come up when you inevitably, or, well, you can keep delaying, but eventually you're going to encounter them if you try to actually integrate your integrand. Okay, so there's a huge body of progress, and for that, I'm also just referring to some recent review articles. What it all comes down to, though, and what we do as amplitudes practitioners, all these techniques rely on controlling the space of functions. So I've talked about some early history, but there's some even earlier history. So the roots of our community, in a way, go back to the whole program of the analytic S matrix from the 1960s. And so this book, which I think maybe many of you are familiar with, also just studies the analytic properties of amplitudes as such. And I just want to show, for example, right, the book is filled with, well, it's filled with words, and then it's filled with pictures that look kind of like this, very complicated. What is a real Landau curve showing that if it were singular in a certain limit, its attached singular surface would be a horn of singularities. I mean, yeah, so that, this is true. And in some work, when we're trying to understand the singularities of amplitudes, even now we do come face to face with some of the old literature where they did appreciate some mathematical structure. But I mean, we do have a more modern viewpoint, and so now we want to bring this forward. But what we learn from this is that, yes, it is hugely important to understand the singularities. That's what allows us to make progress. So analytic properties do provide huge constraints, but what we appreciate more and more and in concrete detail now is that we should really understand what types of functions we're working with. So a theme of these days is to really control the space of functions, not just their individual singularities. This idea of understanding what functions you're working with first and then looking at their analytic properties, this is what underlies the on-shell methods like the unitarity method, generalized unitarity, the idea about quadruple cuts, getting those coefficients that all rely on BCFW recursion, that all relies on knowing what types of poles and branch cuts you expect, and then doing enough pattern matching. So that's still our story. It's just that now we realize we need more and more complicated functions. So that's a big part of our work these days. Okay, so for example, coming back to box functions. So here's a page from our picture from the analytic S matrix. If you want to understand box integrals, in the analytic S matrix book, you'll look at a picture like this. And what they didn't have available to them then, what I want to emphasize is, an actual function that a box integral evaluates to. So I could tell you all about the singularities, where they are, but they would never write down anything like this. And there are a couple of reasons for that. I guess one obvious reason is they were concerned with the theory of the strong interaction. And at the time, that was not understood to include any kind of massless particles, or even massless particles as an approximation. So everything they had was expected to be massive and generic. So there was no dimensional regularization. If you were to write down a box with arbitrary masses everywhere, it would be much, much more complicated than this, even though it's finite. But here, okay, so what I've drawn here, I meant to come through too well. These are two thicker lines. This is a 2-mass hard box. Or you know that terminology, so that means there's multiple, say, particles coming in here and here, massless in the loop, and then 2 massless lines here. Okay, so this is divergent. So I've written it down in the epsilon expansion and dimensional regularization. And when we talk about the function space, we see that if you wanted to expand in epsilon, you get some logarithms from these first divergent terms. And then you see some extra explicit terms with logarithms, and then even a dilogarithm function. So this is actually all that goes into the box integrals. To understand the box integrals in 4 dimensions, you only need to understand logarithms and dilogarithms. So that's what I mean by the function space. But then beyond that, it gets more complicated. So comments to make here is analytic continuation. I mean, the sort of thing they're doing in the analytic S matrix, that's still important to us. We still want to understand how to do that. But also, we're interested in different mass configurations. We have a particular interest in massless particles being part of our theory. We want to control divergences explicitly that arise from having massless particles. And a crucial part of the story recently, and sort of a stepping stone for going forward, is finding understanding polylogarithms, as we see here. So we've had a lot of success in the case of integrals that involve polylogarithms. Polylogarithms are iterated integrals with these simple integration kernels. I want to introduce the symbol. So they have something called a symbol map, which takes a polylogarithm and maps it something in a tensor algebra. And the usefulness of the symbol is that it encodes relations among logarithms and polylogarithms. So you lose some information, but you get some more control, and then you can try to recover the information later. And we've had a lot of success with this because many Feynman integrals are polylogarithmic, not just the 1-loop boxes, but also many others beyond 1 loop. The whole family is known. We also know that there are ones that are not polylogarithmic. So this leads to a program called the symbol bootstrap. Now, I mean, bootstrap in a way, it just means all these shortcuts that we take besides doing direct computation. This has been part of the story of what we do in Amplitudes long before we use the term bootstrap to describe it. But there's a symbol bootstrap for polylogarithmic amplitudes, which I think basically has 3 steps. So if you know that you're working with something polylogarithmic, And you'd want to just write down its symbol in a bootstrap sort of way without computing it directly. You want to know the alphabet, so what's going into that tensor algebra. You want to know how those letters, those alphabets, are combined into words, or what sequences they can appear in, because not all of them will be possible physically. And then finally, you want to put all the coefficients to make the correct linear combination in the symbol. And to do all that, there are many, many considerations that come to bear on constraining your original enormous ansatz for a symbol. And there are also techniques, I guess they're not even listed here, for how to generate the symbol alphabet in the first place. Again, this is a vast subfield, and I'm just citing some review articles there. So if we come back just to the simple problem of one loop amplitudes with now n legs, an arbitrary number. So in principle, this will also be arbitrary helicity configurations once n is sufficiently large. What do we know? Well, we've known for a long time that in the MHV case, not only do you only have boxes, but you only have certain kinds of boxes, 1 mass and 2 mass easy. And the coefficients are simple. So those boxes and their coefficients are all precisely the tree level amplitude, which is the Park-Taylor formula. Next to MHV amplitudes, we'll have all the boxes involved except for the 4 mass box. That doesn't allow an MHV helicity configuration. And their coefficients are also pretty well understood. They're called R invariants. Beyond those helicity cases, though, the coefficients are functions of R invariants. And this is where, as the coefficients get a little bit more complicated to find explicitly, you can pursue amplituhedron ideas. But amplituhedron is also sorted by the helicity category. So, I mean, what we're doing here is at one loop, of course, at one loop, it's still just a quadruple cut. It's just that if you go to more complicated helicity cases, you can't immediately write down these 4 tree amplitudes, but besides just saying that they're the 4 tree amplitudes. So that's where we'd like to be able to say a little bit more. Now, in my view, suppose that we attack this problem, come back to this familiar problem, but we just want to clean it up and use the most modern techniques we can in preparation for going farther. So suppose we want to work in dimensional regularization for one reason that I mentioned before, which is we use it in particle physics more generally. And another reason is that it's also been important to us in the study of the coaction. So suppose we do want to do this in dimensional regularization. Suppose we want to work with arbitrary helicity sectors. The question is, what's the optimal presentation of just this one loop amplitude? So I want to approach this from 2 angles. One is this algebraic structure called the coaction, which includes information about the symbol. And another is using geometry and cluster algebra, more modern techniques. Okay, so now I'll start to write down the symbols of the box integrals, just looking at one loop. So it doesn't all quite fit on a page. So I've started with the divergent parts. So here are by the way, there is a 0 mass box for the 4-point amplitude, right? But let's assume that n is greater than 4. Okay, so there are divergences starting at 1 over epsilon. Then there are, for symbols, there are 1 over epsilon terms, and then there's going to be symbols at weight 2 that we'll come to. Now there's known universal infrared behavior of amplitudes, which is given here. The divergence is proportional to the tree amplitude, and it picks up just the 2 particle invariants. This already, so what we're doing here is we're going to combine all the boxes with their coefficients. And if we don't yet know what the coefficients are, this already implies some linear relations among the box coefficients. If you just put arbitrary coefficients there, there's going to be some constraints that combine these divergences in a way to correspond to this known behavior. Okay, before we talk about combining the symbol, now at weight 2, it's not constrained by the divergent behavior. So at weight 2, this is what you get for the symbols of some of the boxes. I've just put down representative ones. And there are 4 types of symbol letters appearing here. Here I've highlighted them in different colors. So we have, and the most basic kind is just a Mandelstam invariant that appears all over the place. Then there's a symbol letter, which is a difference of two Mandelstam invariants. There's one that's quadratic in Mandelstam. And then there's one that's further, that's algebraic, that only comes up in the 4 mass boxes. So this is just 3 of the 5 types of boxes, but the story is the same for the other 2. Don't get any new types of letters. So now when we combine that all with the correct coefficients, we also want to consider, I mentioned coaction. So coaction is another kind of algebraic structure that's conjectured to apply to Feynman amplitudes in general. And another more recent development is identifying how this works at the level of diagrams, most concretely at one loop also. So this is just an example of how the coaction works diagrammatically, again on a 2 mass hard box. So we take a coaction here. I know I'm not explaining coaction, but this is also a sort of tensor algebra, and it contains all the information about the symbol. So if you understand what's happening here, you can extract symbols and you can extract information about what's going into the symbol alphabet and the words as well. What letters can follow which other ones. So we wrote this down, sort of diagrammatic coaction for our master integrals. Now, what about physical amplitudes? That's the question. So if we want to put this in our simplest, our hydrogen atom of quantum field theories, n equals 4 super Yang Mills, we need to combine these things for symbols with their proper coefficients. So, okay, now I'm coming to, this is some actual work in progress with my student, Nancy Angelopoulou, and with Matteo Parisi, who is, I think, on his way to this conference in a couple of days, I hope. So what we find when we do this is, okay, no surprise, we verify the first entry condition. You can see this from boxes. First entries are just, have to be the Mandelstam invariant letters only. Now we have 4 types of letters, and they can appear in the second entries of the symbol. This is just at weight 2 now, which is our non-trivial part. Of these 4 types, the quadratic and the algebraic 4-massed ones, they come only with very unique boxes. You saw where they show up. So they really label their boxes and their coefficients. So that's easy. These ones that are differences, they end up dropping out in the whole sum. So this is some cancellation that's not visible at this level of the box expansion. You have to discover something else about the full amplitude in order to see that. And what's left is just the Mandelstam invariants. And so then we have words that are Mandelstams times other Mandelstams. So I want to comment on this, the letter that's the difference of Mandelstam invariants. Okay, so there are reasons you might expect them to be absent. First of all, if you're expecting a cluster algebra structure, they don't correspond to cluster variables, so that doesn't fit. Okay, the cluster structure isn't really proven in general. It's a very tantalizing set of conjecture, but it could break down somewhere. They're also not compatible with dual superconformal symmetry. But again, we're not sure if that applies directly because we're working in full dimensional regularization. So what does really assure us that they do drop out is we have a bottom-up proof of this cancellation from a sort of BCFW type momentum shift for this relation here. So if you start from, we don't have a 2-mass triangle, but if you start from that configuration of legs, then there are two ways to expand this triangle into a box. That would be part of your master integrals. And the statement is all the coefficients you get from one of those ways sum to the same sum that you get from expanding this the other ways. And this will be familiar to Andy and Gab from their old work. They found this relation, although they derived it differently from dual superconformal considerations. So this is nice just to see that we have a way of generating relations that sheds light from a different angle on why this cancellation happens. This relation also, I point out, this has a geometric interpretation in terms of 2 different but equivalent dissections of a boundary of a loop amplituhedron. That can be seen, again, amplituhedron is sorted by helicity sector. So this is concretely true for NMHV. We can conjecture that it holds beyond that. Okay, then the remaining words are just these Mandelstam times Mandelstam ones. So we also classify their coefficients and try to clean them up as much as possible. And there's some statements we can make. So if you have 4 distinct indices, really like 2 totally different invariants, then the coefficient is either 0 or a single box, because now you've cut in 4 different places, so that gives you a box. At the other extreme, you could have just 2 indices, meaning a repeated letter. In that case, what you get for the coefficient, I'm saying, is just what you get from the maximal cut part, or half of that in the case of a 2-particle invariant. What I mean by the maximal cut part is just a contribution from the leading Landau singularity. So here, where this appeared, the quadruple cut, in the full diagrammatic coaction, if we just focus on those terms. So this is what gives you the quadratic terms, the quadratic letters for certain boxes. But for other boxes, those quadratic terms degenerate, and they're just products of 2 Mandelstams. I mean, that's a quadratic one, but then you can factorize it further. So that's why some of those land on these letters, exactly. So here, the more complicated case is what's in between. If only 3 out of these 4 indices are distinct, then you get, generically, you get a combination of different 3-mass box coefficients, which also simplifies. So okay, we know that that's going to be 0 for in the MHV case. In the next to MHV case, it's just a difference of 2 R invariants. And the interest in noting that is that it exposes some features of cluster adjacency. So we just have some comments on cluster adjacency. Again, I can't explain cluster algebra. I'm just making this comment here. Cluster adjacency is a relatively new principle for n equals 4 super Yang-Mills amplitudes that's associated with various conjectured manifestations. Basically, the question is the amplitude, or to what extent is the amplitude assembled from so-called cluster variables in patterns that are further constrained by cluster algebra operations? So we, in this project, we're exploring a conjecture by Gurdwan and Parisi, which is based on amplituhedron geometry of cluster adjacency of poles of the coefficients and the maximal cut Landau singularities. So here, just at weight 2, right, we've got 2 letters, and then we've got the coefficient of the word. So there's, among all these 3 objects, you can discuss how they're all pairwise cluster adjacent, or whether the poles sit together in the same cluster. So, okay, so there's a specific conjecture relating to the maximal cut part, but more generally, we are finding that it extends to the other terms that are not coming just from the maximal cut part. So we've checked this for NMHV beyond the maximal cut part. So I mentioned in the previous slide where the coefficients have these 2 R invariants, and we also hope to be able to extend this idea beyond NMHV. It all comes back to, in a way, what's the best basis? And this is a question, I think, that comes to many of us in many, many different contexts in the study of amplitudes as well. So I'm coming to this question because for our case, okay, well, so for n equals 4 super Yang-Mills, right, we have this specialized basis, restricted set of master integrals. In dimensional regularization, I mean, also a very active area of research now is looking for canonical bases. So that's where they satisfy special differential equations. Our diagrammatic coaction, which we hope to extend more solidly beyond one loop, that also uses a somewhat different basis. I was just showing the same boxes, but actually the coaction uses diagrams that are in different dimensions. So even at one loop, it's not the same box basis. In the one loop calculation I was just discussing here, we do like boxes, the classic box basis, but I mean, there's that issue of the cancellation, right? Some of those letters canceled out, which means maybe we should be looking at a basis, if we're going for n equals 4 super Yang-Mills, that didn't have those parts to begin with. That's the sort of thing we're always looking for in amplitude. And, maybe there are other answers. So for the diagrammatic coaction in particular is also an open question going beyond one loop. What is the right basis in which to express the coaction principle? So to sum up this talk, planar n=4 super-Yang-Mills continues to claim prime importance in the field of amplitudes. Many of us keep coming back to it from time to time. And I think there's a lot more to understand, even starting back at one loop. Future directions related to the topics here are to formulate and then use diagrammatic coaction beyond one loop integrals, more loops. And actually, the driving question here is, does some version of the diagrammatic coaction really carry over to the amplitude level? Right, so that's one motivating question. Can we lift it to a coaction that includes these coefficients in a meaningful way? Then, we're also looking beyond polylogarithms. This is already in progress, so we want to understand the relations there. And very broadly, an ongoing project is understand how to control the function space using everything we know about what functions do appear and things we continue to learn. Now also, of course, cluster algebra and amplitude-Hedron geometry, these are very interesting. And if we could find a way to extend these lessons, preferably in a way where we don't have to do every helicity sector separately, that would be fantastic. And as always, and for all of us, our job is to apply all these lessons we learn in n=4 super-Yang-Mills to all the other theories of interest. Thank you.